Welcome to the presentation of LatentCLR, a contrastive learning approach for unsupervised discovery of interpretable directions. I am Oğuzkan Yüksel, and this is a joint work with Enis Simsar, Ezgi Gülperi and Pınar Yanardağ. Recent research has shown that it is possible to find interpretable directions in the latent spaces of pre-trained generative adversarial networks. These directions enable controllable image generation and support a wide range of semantic editing operations such as zoom, rotation, facial features, pose, or changing hairstyle. In this work, we propose a contrastive learning-based approach to discover semantic directions in an unsupervised manner. LatentCLR consists of three parts. First component is direction models that take latent codes and apply a directional edit to this input latent code. Fixed directional edits, as well as neural network-based models that can conditionally adapt the direction based on the original latent code are considered. Second is the pre-trained GAN and a selected target feature layer in this GAN. This feature layer is used to disentangle directions proposed by the direction models. Third component is the contrastive loss function based on the normalized temperature scaled cross-entropy loss. It uses an inner product as similarity measure, but works on n tuples of positive samples instead of doublet of positive samples. Given these components, LatentCLR works as follows. First, the latent code is passed through all the different direction models to obtain directional edits. Second, all of the obtained latent codes pass through the generator up to the target feature layer. Same feed-forward operation through generator is applied to the original latent code. Obtained feature representations are used to calculate the effects of each direction model on features by a simple subtraction. Same steps are executed for all the latent codes in the batch. Given these feature divergences, the contrastive loss function is applied. Feature divergences yielded by the same source direction model are considered positive, while the rest are considered as negative pairs. As each direction model is applied to each code in the batch, there are in total n positive pairs for a single direction. The aim of the contrastive loss function is to establish unique footprint in the target feature layer for each direction and establish semantic disentanglement. For evaluation, we apply our method on StyleGAN2 to a wide range of datasets, including FFHQ, LSUN horse, cars, and cats datasets. We observe that our method is capable of discovering several fine-grained semantic manipulation directions, such as changing age or race, adding riders, changing car type or scenery, changing breed, or adding fur. We also evaluate our approach using a pre-trained BigGAN model that is conditionally trained on 1000 ImageNet classes. Our model is able to detect several semantically meaningful directions such as zoom, rotation, contrast, as well as some finer-grained features such as background removal, sitting, or green background. The directions found by our method are highly transferable between ImageNet classes. For instance, the directions learned from the Bulbul class are able to rotate a goose and add greenness to castle classes. An interesting transferred direction is sitting, which manipulates the latent code so that the bird in the Bulbul class sits on a tree. When applied to the class bulldog, this direction also causes the dog to stand up or sit down. Results of our method on FFHQ dataset are competitive with other state-of-the-art unsupervised methods such as Cepha and GANSpace. To understand how our method compares to the competitors in quantitative terms, we performed a risk scoring analysis using predictors released by StyleGAN2 for smile, age, and lipstick attributes. All methods achieve similar changes in scores of classifiers over 500 randomly generated images. Our implementation is available at GitHub. Thank you for listening.